Today we're going to be talking about benzylpiperazine, also commonly known as BZP. Alright, so let's dive right into it. So a quick intro to BZP. Benzylpiperazine is a derivative of piperazine, and piperazine is an industrial chemical that has a plethora of uses, including in the manufacturing of plastics, resins, and antimicrobial agents. In our case, piperazine is a precursor to benzylpiperazine, the drug of abuse we're going to be investigating today. And benzylpiperazine is classified as a designer drug. And a designer drug is essentially a drug that is either a structural or functional analog that mimics the pharmacology of a controlled substance. In our case, benzylpiperazine is a functional analog to amphetamine because both share similar psychoactive properties. They're both stimulatory and they alter wakefulness and attention. And an interesting thing about designer drugs is that they avoid classification as a legal drug because they're derivatives of compounds. This is the reason why designer drugs are becoming an increasing problem because there is a latency in legal classification. Similarly, amphetamine shares similar pharmacodynamic properties to BZP, and they both share similar mechanisms of action. Alright, so just a quick look at a couple of the pseudonyms that BZP goes by. Rapture, Herbal Ecstasy, and Legal X. And Legal X is a misnomer. And they call it Legal X because of the latency of regulation that causes a lot of people to start to abuse benzylpiperazine. And this increase in abuse mushrooms the prevalence of these drugs of abuse. And many times, NMDA and amphetamine drug abusers begin to use BZP as a substitute because these drugs share similar subjective experiences. All right, so before we dive into the pharmacokinetics and pharmacodynamics of benzylpiperazine, let's establish context and look at the history of BZP. So it all began in 1944. BZP was synthesized in the Wellcome Research Laboratories in the UK, which was a major research center at the time for pharmaceutical research. And the purpose of synthesizing BZP was to see if it had any antiparasitic properties to treat roundworm infections. But because of the low efficacy and adverse side effects, it didn't warrant the trade-off. However, in the 1970s, BZP was rediscovered and it was examined for its therapeutic potential as an antidepressant, acting similarly to many SSRIs and increasing synaptic serotonin levels. But again, it was not pursued because of the high abuse potential. And the problem really began in the 1990s, when New Zealand youth popularized the drug, colloquially classifying it as Legal X. And this drug was used in the nightclub and rave scene. And today it's also used in the nightclub and rave scene. And the US caught on. And in 2002, the US temporarily classified BZP as a Schedule 1 drug because of the high abuse potential and no redeemable medical benefit. However, there's a slight conundrum. This was based off the idea that the potency of BZP was 10 times that of amphetamine, when in reality, BZP was actually 10 times less potent than amphetamine. Despite this, in 2004, the US permanently classified benzylpiperazine as a Schedule 1 drug, which extremely limited their access and led less people to abuse the drug, at least in the US. However, because of the latency in legal classification, BZP abuse was still a very large problem in New Zealand. And in 2007, it was reported that 5 million BZP pills were sold in New Zealand. And in a similar survey at this time of 18 to 29-year-olds, 40% of them have attested to trying BZP. And the hammer came down in New Zealand in 2008 when New Zealand finally banned the sale and possession of BZP, which decreased the amount of users of BZP, but unfortunately it led many BZP abusers to other drugs like NMDA and amphetamine. Alright, so now let's examine some of the pharmacokinetics and let's study how there are individual differences in the metabolism of benzylpiperazine. So the most common mode of administration is orally via a tablet. However, there are other modes of administration: inhalation or snorting, insufflation or blowing something into your nasal cavities, and IV administration, which is the fastest route, but it's actually the least commonly used because of the alkalinity of the substance, which induces physiological pH that lead to adverse symptoms like metabolic alkalosis. Let's look at the half-life. So in this figure, you can see the half-life of BZP at around 330 minutes, or about 5.5 hours. And it's reported that the subjective and physiological effects are reported at about 1 to 2 hours of oral administration. And the effects can actually last to about 4 to 8 hours. However, there's variability in abuse potential, and this variability might have metabolic implication. It appears that BZP is metabolized by the enzyme cytochrome P450, which has susceptibility to genetic polymorphisms. And it's these polymorphisms and variability in the genetic expression that might lead to differences in dependence of benzylpiperazine. All right, so now let's look at the pharmacodynamics of BZP and how BZP affects brain function and neurotransmission. So it's reported that BZP acts as an indirect agonist that increases the levels of monoamines, which we know are dopamine, serotonin, and norepinephrine, and it increases these levels in the synaptic cleft. And the mechanism behind this is that BZP binds to monoamine transporters at aminergic cells and blocks the reuptake of those monoamines, thereby increasing the levels of the neurotransmitters in the synaptic cleft. And let's take a quick look at how this works in dopamine neurotransmission. So here's a figure of the postsynaptic cell and the presynaptic cell that has the dopamine neurotransmitters along with the dopamine transporters. And what BZP does, it invades the synaptic cleft and binds to the dopamine transporters, causing the inhibition of the reuptake of dopamine, leading to the overstimulation of the postsynaptic cell. And let's look at a quick question. Which other drug increases aminergic concentration of dopamine in the synapse via similar mechanisms to BZP? Is it A, ketamine, B, spice or synthetic cannabinoid, C, morphine, or D, cocaine? And the answer is D, cocaine. And we have seen this in class, that cocaine binds to the dopamine transporters and blocks the reuptake of dopamine. However, BZP also acts as a non-selective agonist, and it binds to serotonin receptors and their different subtypes. For example, BZP binds to the subtype 5H2A of the serotonin 2A receptor, and this is involved and it's implicated in the mild hallucinogenic effects of BZP, which is why I classify BZP as a really messy drug because of these different mechanisms of action. All right, so now let's look at the behavioral effects BZP has on the body and the behavioral effects. So some of the acute effects that are examined is mild hallucinogenic effects that are mediated by the serotonin 2A subtype that we just seen. There are also stimulatory effects, which is mediated by the mesolimbic system when the VTA projects to the nucleus accumbens. Euphoria, which is mediated by serotonin. It's also involved in increased alertness and increased sociability. And these are similar effects as amphetamine, which we know is the ADHD medication. There's also tachycardia, or increased heart rate, and hypertension, which is mediated by the activation of the sympathetic nervous system. Now let's take a quick look at some of the chronic effects. So the cardiovascular aberrations due to chronic sympathetic effects that leads to cardiomyopathy and might lead to myocardial infarctions. There's also serotonin syndrome, and these symptoms are associated with the constant blockade of serotonin transporters that leads to migraine and headache. There's also metabolic acidosis due to the disruption of the physiological pH that increases CO2 levels in the blood plasma, causing hyperventilation. So let's take a quick look at this video. So there you're able to see BZP in action, and you're able to see some of the stimulant effects of BZP. Thanks for watching.